First of all, Ethereum is awesome.
At a high level, the design is very simple, it's very beautiful.
If all people store their money on exchanges on this hot wallet, then it doesn't really matter. Then it's a blockchain. It's really easy to get into Ethereum, right? So let's build this thing, right?
Hello everyone. My name is Aki Moritani. It's my pleasure on behalf of BBOD today. So we are delighted to have you with us for tonight Blockchain Cambridge seminar. Thank you for coming. And just before we get started, I would like to express my gratitude to all of you who genuinely help us make this event come together so smoothly. And of course, I'd like to give special thanks to today's speakers, Mr. Frederick Liu, Mr. Ivo Zielinski, and Mr. Justin Drake. Now, I will hand you over to BBOD co-founder and chief economist, Piotr Arendarski.
Welcome. My name is Piotr Arendarski. I'm a chief economist and co-founder of BBOD. It's my pleasure to host so many people. This is our first meetup, so I'm very excited. So today I will have a very short speech. I will introduce this meetup and I will introduce BBOD, which is our main sponsor. So Blockchain Cambridge meetup should be in our opinion, it's our goal, it should be a hub for people who want to come to the meetup and meet outstanding Cambridgeshire UK blockchain companies. Okay, so we will invite, with the help of Hazem, my friend, the best Cambridgeshire UK blockchain companies. Occasionally, we will invite another companies from other countries like Korea, Japan. So let me introduce BBOD. BBOD is hybrid decentralized cryptocurrency exchange. It's a little bit difficult sometimes for some people to grasp what does it mean. Maybe you know what is cryptocurrency exchange. Maybe you know what is how to trade on Binance. It makes hybrid and decentralized a little bit different to grasp. So let me explain. Decentralized means that BBOD offers secure on-chain custody and settlement. So your coins are not custodied by the exchange. Your coins are stored in smart contract under the blockchain protection. Okay. And additionally, our smart contract settle every day profit and loss from your trading or exchanged asset. Okay, but Ivo Zielinski will explain you a little bit further this concept. So on the top of the blockchain technology, we offer fast off-chain matching engine.
There's like a very specific application-focused, application-centered blockchain, which is called Ethereum. And on Ethereum, you can build basically applications which are totally distributed, decentralized, and you use smart contracts to achieve that purpose, right? And yeah, that's what that app is. And oh, you didn't see anything. Okay, so my speech is about hybrid dApps, and it's going to be a very high level, not very technical, heavily opinionated, and I hope you all like it. Okay, so a few words about myself. My name is Ivo Zielinski, and I've been working in the space since 2016. I've been helping various clients from the ICO space and from the corporate space to sort of bring the value of the blockchain to their business. And I work at Indoors full-time, and also working with BBOD to develop the decentralized custody system for their exchange. Okay, so if you want to hit me up or have a chat, just send me an email. I'll be happy to connect. Right. So the outline of this presentation, first I want to talk about my first sort of experience with Ethereum from the perspective of a software engineer, and sort of what inspired me about it, and then how I sort of started digging deeper into it and discovered the limitations of the platform. And I want to make a case for sort of like a hybrid approach, so like a mix between a centralized application and an app. And I want to quickly analyze a case study of the exchanges. So first of all, Ethereum is awesome, right? So when I first started to learn about it, from a developer perspective, it's a really easy platform to get into because you forget about all the problems that you had, all the mundane stuff that you have to do, like all the database operations. You don't have to worry about the data consistency. Everything is sequential. We have identity out of the box, so it's all handled by math. So asymmetric cryptography is handling your user registration because your users are basically public keys, or in the case of Ethereum, is address. You don't have concurrency problems, it's sequential, so you can really focus on the logic of your applications, right? And also it's programmable money. So you have this value network, which is Ethereum and Bitcoin, and you can really do amazing stuff with it. So automatic bonds, automatic dividends, all sort of stuff, very inspiring stuff to do. And the wonderful ecosystem on top of it, so all the tools, it's really easy to get into Ethereum, right? So let's build this thing, right? So, okay, but then you dig into this, deeper into this ecosystem, you start building smart contracts, you start building your dApp. Then you realize there's like a huge cost that you have to pay, right? So every operation that your users are making, every operation that your system is making, you have to pay for it, right? And then you have the performance problems, so the transactions take long to confirm. Also, you're limited to 15 transactions per second, which is not even enough to accommodate like a medium-sized company, right? Also, the user experience is pretty bad. There's a steep learning curve, and getting into the system, you have to install a wallet, you have to understand how to handle your funds securely, how to store your wallet. Maybe you have to install some like bizarre plugins to your browser. It's all very, very confusing for new users. And so what I realized about Ethereum is that it's not really like a server bullet, right? It's not really either a database or a server. It's not meant to replace the legacy systems, the Web 2.0 with something new, at least not yet, right? It's not ready for it. And I think it's a blockchain, right? So it's a very specific tool for very specific applications that has to be used, just another tool in the programmer's toolbox, right? And you really need like a good use case to use it. Okay. So also I think the limitations of Ethereum are what makes it fun to work in this space. So you can really be creative instead of making another database migration or a user registration system. You can actually invent those clever workarounds around the limitations of Ethereum. And there's a lot of very exciting research going around, scaling the current Ethereum implementation, so the Plasma, the state channels that you can actually implement yourself. So it's really fun. It makes programming fun again, for me at least. Okay, so we made some really great progress from the Web 2.0, like from the centralized big apps, which really gave us great value. So we moved from that to Ethereum Bitcoin, right? But we cannot we're not in the level where we can this sort of supercomputer that we can use to compute all the social interactions and tokenize everything. It's not really possible. The tech is not here. We cannot have the blockchain cities, although some people are attempting it. And we're sort of like at the beginning of this journey, right? So I don't think like it should be an excuse for developers to wait for all the scaling to happen. And we can still make this the current applications, the current systems, because people are using much better with the tech that is already here. Okay, so what is like a hybrid DApp? So to explain this, I'm going to use like an analogy from the past, from one of my past clients. They really wanted to have their PDFs on the blockchain, right? So they fear that having things on the blockchains makes them 10 times more valuable. It makes it much better. It's excellent to have everything on the blockchain, right? These are some internal reports, invoices, that sort of stuff. Okay, so what is the benefit of having your invoices or your certificates documents on the blockchain, right? So they're actually immutable. They're tamper-proof. No one can modify it. No one can refute that they actually have been uploaded at that specific time. And they're available. So they are alive as long as they can be retrieved from the network as long as the network is alive. So it's pretty awesome. But at the current state of Ethereum, storing an actual PDF or big file on the smart contract is really expensive. It's actually not viable at all. So not only would pay a lot of money, it might not even fit in a single block, and also you lose the privacy, right? So what if you put something on the blockchain once, you compromise all the information. There's some confidential information that PDF, you lose it because it becomes public, right? So it's not really viable to have a PDF chain, right? Currently on Ethereum, right? So what you can do is you can do something really simple. You can take the PDF, take the file, just use a one-way function, save the hash in a smart contract, and store the actual PDF somewhere else. So effectively, you get like a hash pointer. You have the hash on the blockchain that is pointing to a resource that is stored somewhere else. You still get some value out of it. You sacrifice some decentralization aspect of your PDF chain, but you maintain the immutability and the refutability aspects. You lose the availability because once the external data store goes down, your PDF can no longer be retrieved, right? But it is possible right now, and you could create this sort of application right now with the current state of tech. It won't be too expensive. You can actually make it much better, and you can improve whatever your client was doing with your PDFs. You can decentralize it, make it much better, and you can do it with this current state of tech, right? So you don't need Plasma for that or sharding, right? So when it comes to exchanges, so on this side we have the spectrum of decentralization. So on the left there's fully decentralized solution on Facebook, and these are not really exchanges, but they are centralized. On the right we have fully decentralized dApps, which are decentralized exchanges operating fully on the blockchain, right? So the exchanges are usually the type of applications that are the entry points for most of the users. So usually the first contact is to buy a Bitcoin or sell a Bitcoin or speculate, do something with it. And these centralized exchanges are used by most people because they're easy to use, right? But they're not decentralized, right? So on this slide you can see this is like the list of top Ethereum wallets, and as you can see, the first wallet is actually from a centralized exchange, Bitfinex, and contains 1.453% of all Ether that exists, right? There are many more of these wallets. So as you can see, many people are just using those exchanges to store their cryptocurrencies, which truly defeats the whole purpose of cryptocurrencies, right? Because if all people store their money on exchanges, on this hot wallets, then it doesn't really matter that it's a blockchain, right? The transactions are just really like bits flipping in some other database, and doesn't even matter that it's a blockchain like behind it, right? And also these exchanges are like huge targets for hackers. So the more people store crypto on an exchange, the higher is the return of investment for a hacker to attack this exchange. There's very expensive attacks to destroy this exchange, extract, steal all the money, right? And we've seen that happen. We've seen like Mt. Gox from 2014. It wasn't a hack, it was something else. But anyway, there's a single like entity going down, and a lot of people losing money, right? And we don't want this to happen because it makes no difference from the current financial system, which also is very flawed. On the other hand, you have the decentralized exchanges where all the assets, all the Ether is stored in a smart contract. Everyone has protected by the private key, so everyone is their own bank. And there are some very brilliant solutions of how to do this multi-party transaction signing and handle all this matchmaking and execute the orders off-chain. And it's very cool and awesome, but you are still limited by the throughput of Ethereum, right? So Ethereum can handle 15 transactions per second. And this is the maximum amount of trades that can happen on all the decentralized exchanges in this ecosystem, right? So it's not much. It's not really enough. Also, you have this UX problem, right? So to use these exchanges, this requires you to install some plugin. You have to understand how the whole transaction signing works. Then you have to understand some obscure terms like wrapping Ether and converting it to an ERC20 token and transferring it to some, it's very complicated, right? So users usually opt into a centralized exchange because it's much easier to use, and they just need to make a wire transfer to a bank account. Then they can start buying Ethereum or speculating on cryptocurrencies, right? So what I'm trying to show is that we can use the same analogy with PDF chain, right? So we can take some aspect of the decentralization that we can actually achieve at the current state of the technology, which is the storing user assets in a smart contract. Right? So that's the thing we can do right now, and to have the full security of the blockchain in a smart contract, and then we can move other things that we cannot decentralize yet off-chain, and which we have excellent existing systems to use, and actually make the UX much better. So withdrawals and deposits are using Ethereum transactions, but all the trading is actually happening off-chain. Right? So you can actually sacrifice some decentralization for the better experience. I think this approach is much better than a fully centralized exchange, and I hope I convinced you. And yeah, so thank you for your attention. And do you have any questions?
Justin will introduce something revolutionary concept in my mind, which is Ethereum 2.0 network. So now we have Ethereum 1.0, and Justin will talk about Ethereum 2.0, which will be far more faster and better.
Okay, so I just want to draw a picture of what Ethereum looks like, so I can communicate some of the basic ideas of Ethereum 2.0, because at a high level, the design is very simple, it's very beautiful, and I hope to communicate that. And then if I have a bit more time, I'll delve into some more advanced topics. Okay, so what are we assuming for Ethereum 2.0? First of all, we're assuming that we have the current Ethereum 1.0 blockchain. So this is what we have, and the end goal is to try and have basically multiple blockchains, what we call multiple shards, so 1,000 shards. So I'm going to try and draw the shards here. So we're going from one blockchain to multiple blockchains, and we're going to about 1,024 blockchains. So the goal is to try and increase the scalability at the consensus layer by a factor of 1,000. And at the architecture level, what we have in the middle between these two things is the beacon chain. Okay, so the beacon chain is a part of a system infrastructure, which is going to help organize how the shards work, but in terms of all the application, transactions, and the state, these will live in the shards. So each state is its own little universe. It has its own mempool and basically blockchain, and it has its own state. So one important thing about Ethereum 2.0, which is basically from here downwards, is that it is a proof of stake system. So we have what I call validators, which are the main participants in the system. So how do you become a validator? So we kind of have this pool of validators. Yeah. And the way that you become a validator is by making a deposit from the Ethereum 1.0 chain into a special contract. So you will deposit 32 Ether if you want to become a validator, and after an induction period, you will be part of this pool. Now, the way that the proof of stake system works is that it basically is a new way of picking participants in the system to do work. So if you think of proof of work, one way to think of it is that you have this virtual pool of miners, and then you have this mechanism, the mining, which is a way to fairly and randomly sample miners. So here, instead, what we have is we change the nomenclature, which is validators. Instead of having hardware, you have stake. But in a similar fashion, we have a process of randomly selecting validators. So one of the things that the beacon chain does is that it produces randomness. Okay, so at a regular interval, you have these random numbers which are generated in a decentralized fashion, and they're meant to be unpredictable, unbiasable, and you're meant to have a constant stream of them. And then using this randomness, what you do is that you are going to sample validators and assign them to shards. And also you're going to assign some of them to the beacon chain. And so this is one of the key ideas of sharding, is that in order to reach scalability, instead of every single miner working on the same data structure, Ethereum 1.0, what we're going to do here is we have this pool of validators, and we're going to assign different validators to different shards. Okay, and so as a single validator, you don't have the full picture of all the shards. You only are working on one shard at a time. Okay, so let me talk a little bit about how these shards are connected to each other. So you have what I called crosslinks, because one of the goals of sharding is that the different blockchains talk to each other. So you have these validators that are assigned to the shard, and they will start growing the shard forward, proposing new blocks. And then at regular intervals, you basically want to have checkpoints, which we call crosslinks, go back to the beacon chain. So in terms of the various roles, those who extend the shards are called proposers. And those who create these crosslinks are called notaries. Crosslinks made by notaries. Okay. And one interesting distinction between the proposers and notaries is that the proposers, they're kind of sampled randomly from this pool of validators on a one-by-one basis. So you have your blockchain, which is growing like this, and then for each block you have a randomly sampled proposer. Whereas the way that the notarization process works is that instead you have a committee. So the interesting thing about committees is that if you have a large enough committee of validators, and the committee is sampled randomly, then that committee is going to be statistically representative of your validator pool. So one of the assumptions that we make in the validator pool, which is very similar to proof of work. So in proof of work, we assume that 50% of the mining power is honest. And here we make a slightly different assumption. We assume that 2/3 of the stake is honest. And then when you sample 1,000 validators from this pool, which contain hundreds of thousands or even millions of validators, then with extremely high probability, at least half of these validators will be honest. And so what we do with the notaries is we basically ask them to look at various segments of blockchains, so of the shards. So we have the shards here, and then once you have a group of shards here, you sample a committee and you ask them to go download all the data here. And what they will do is they will make a vote. So you have 1,000 notaries, and they'll start voting on this segment of the blockchain. And if you manage to get at least 500 votes, that means that there's at least one honest notary who's been able to download all the data. And that means that the data can indeed be downloaded, the data exists, and so it becomes safe to create a cross-link into the beacon chain. So it becomes safe for the system chain to consider this data part of the Ethereum 2.0 state. And so once you have these crosslinks, they are very small data structures. They're just like a hash and some signatures. Once you have these crosslinks, it becomes possible for the shards to communicate with each other. And the reason is that each shard is knowledgeable about the crosslinks that have been made in the beacon chain. And so if something has happened in this shard and this shard here is interested about the state, well, what it will do is they'll say, hey, beacon chain, what is the last crosslink that you have for this shard? And then based on that, I can make an appropriate action in this shard. So yeah, that is basically most of Ethereum 2.0 at a high level. Any questions so far?
When this will be, sorry.
Go ahead.
No, just I was wondering when this will be online, because at the moment we're still on the Ethereum 1.0. And
yes.
It's 1 year that they're talking about having proof of stake. But,
Yes.
Yeah. You know the
timeline. Yes.
Yeah.
Okay, so I've made this public prediction several times now, so I'll just make it again. The beacon chain, so it will have a phased rollout of Ethereum 2.0. The beacon chain, I believe, will be available in 2019. And then that's phase 0. And then phase 1 will be where we'll have the shards. And I believe that will happen in 2020. And then there's actually 2 parts in the shards. And this is part level. So we have, what we're doing is that we're separating the data layer from the state layer. So if you think of blockchains kind of abstractly, what they're trying to do is to solve a consensus game. So you have a bunch of people and they want to come to consensus, come to agreement about something. And what they come to agreement, for example, in Bitcoin or in Ethereum 1.0 is the state of a ledger or the state of a virtual machine. But it turns out there's 2 different things going on. On the one hand, they're coming to agreement on the raw data, the blocks, which contain the transactions. And then they're doing a second step, which is interpreting the data and executing the transactions. And it turns out that the really hard part from a consensus standpoint is the data. And the reason is that there's no unique answer as to what data could be coming in, because you have people around the world and they're kind of unpredictable. Having said that, the execution is much easier, because once you have the data and you have the rules of your virtual machine, then it's just a matter of it's a deterministic function of taking the data and producing a state root, or the state of your virtual machine. So what we're going to do is we're going to actually launch the shards in two stages. Phase 1 will be just the data, which is the harder part. And then we're going to have phase 2, which is where we'll introduce the EVM 2.0, the second version of the virtual machine. And I believe that will come in 2021.
The coin will be the same.
Bitcoin should...
No, the coin, I mean the ETH, the
coin
will be the same, or you will also...
Yeah, so it'll be the exact same coin. So, you have...
There will be no swap, it's exactly the same as this today.
Yes, so all the coins will be fungible. This system is powered with the same token as this system. Yeah.
Yes.
So how quickly are states shared between each of the blockchains on there?
Okay, so how quickly the states communicate from, let's say, from here to here and then back to there?
Yeah. So
Okay.
when to request a cross-link, it's like how old is that person communicating?
Okay, yeah. So the time between the blocks is what we call the slot duration, which is 8 seconds. And then we're looking at a cycle, which is a segment of the blockchain, which will be cross-linked, 64 blocks. So that is about 8 minutes, a bit more than 8 minutes. Yeah, and then you need to factor in a little bit of time for the cross-link, which is actually created off-chain from the point of view of the beacon chain to go on-chain.
Yeah.
And then for it to be readable. One of the interesting things is that, so let me talk about the process of data in a more granular fashion. How do we go from a user transaction to something which is cross-linked into beacon chain? So just like Bitcoin, you have users that generate transactions. These are signed messages. They're broadcast at the network layer. It's a peer-to-peer network, a mesh network. And then these transactions get picked up by the block proposers that were randomly sampled from the validator pool. There's one block proposer per slot, and they will basically assemble the transactions and build a block. That block will be building upon a previous block. And one mechanism that I didn't talk about is attestations. And so this is done by so-called attesters. So one of the problems with the mechanism of block proposal is that you have a single entity, the block proposer, who has monopoly power over the next block. And generally, this is bad because there's some percentage of the validators in the validator pools which will be bad guys, and they'll try and disrupt things. And so one of the mechanisms that we have is attestations, which is very similar to the cross-linking from the notaries, but it happens on a block-by-block basis as opposed to on a cycle-by-cycle basis. And what are the kind of things that you can do which are bad as a block proposer? One of the things you can do is that when you're invited to make a new block, instead of building on the parent, you want to try and do a double spend. So you'll build upon some ancestor, let's say this one, that is kind of deep in the past. And you can try and do this attack and hope that more people will build after you. And it's actually especially bad because one of the properties of the randomness that we have here is that it has a notion of look ahead, meaning that you can't predict, well, you can predict, you do know what the randomness will be up to some certain point in the future. After that, it becomes unpredictable. And so it's possible to know what will be the next few proposers for the next few slots. And so if it just so happened that an attacker, let's say, had the next 4 slots just by luck on a single chain, that means that they could basically build the next 4 blocks here and revert these 3 blocks. And that would be bad. And so what we have is that we have these committees of attesters where for every single block that is produced, they will go ahead and vote. And so for each of these, you'll have votes coming in. And the way that the consensus mechanism works is using fork choice rules. So you might be familiar with the fork choice rule with Bitcoin, which is if you have some sort of fork in the blockchain, which fork do you choose? Well, you will choose the longest chain. It's actually a simplification. You actually choose the fork with the most proof of work. But let's say for simplification, then you choose the longest chain. In the case of Ethereum, what we're going to do is we're going to follow the fork with the most attestations. Okay, and it's what's called last message driven, meaning that we will only consider the very last vote from the attesters. So if they make conflicting votes, so they vote here, and then they make a second vote here, we'll only consider that second vote. And one of the nice things of attestations is that it provides what I call pre-finality. So you may have heard of Casper, the FFG, the friendly finality gadget. So the idea of Casper is that you want to have pieces of the blockchain which are final, in the sense that if they were to revert for some reason or another, at least 1/3 of the validator pool would get slashed. And slashed just means that they lose the 32 ETH that they put down as collateral. Okay, so this is extremely strong economic finality, because we're expecting that the validator pool here will contain billions of dollars of ETH. And so slashing 1/3 of it, that is a huge amount of value which would be destroyed. But before we get to this really strong finality, which happens at the beacon chain level, we will have pre-finalization, where you can look at the attestations, and because the attesters work in committees which were randomly sampled and which are large enough, if you have sufficiently many attestations for a block, then you can basically consider it final. And so this is one of the really nice things, where we have pre-finality on the order of one block in Ethereum 2.0. So you produce your transaction, it gets into a block, and then a few seconds later you have all these votes, these attestations rushing in. And then if you have sufficiently many, then you know that for all intents and purposes, with extremely high probability, that block will be final. Even though the process of finality only happens after the block containing the cycle gets cross-linked, and then the beacon chain, which itself is a blockchain, gets finalized at a point after the cross-link was included on-chain.
You've got all these chains growing at 10,000 blocks a day. Does that go on forever, or do they sort of get you tired at some point and do you create more chains?
Right. So the process of creating blocks is continuous, just like Bitcoin or Ethereum 1.0. But the blocks tend to be data that is discarded pretty fast. So what we really care about is the state. Right, if you have Alice sending money to Bob, she'll make a transaction for that, and then you have Bob sending money to Alice. There'll be 2 transactions in total, but the only thing you care about is the balances. Yeah. So in the case of Ethereum 1.0 and Bitcoin, you have a linearly growing state. So in the case of Bitcoin, you have a block size, for 1 megabyte. And so you can put a cap on how much the state will grow per unit of time. And in the case of Ethereum, it's similar. You have a gas limit, and so that puts a cap on how fast the state can grow. But in the case of Ethereum, you have a dynamic gas limit. So the miners can vote to increase the gas limit, and so in theory, you could have a very fast growing state. This can be a problem, like a large growing state. So just to give a bit of an order of magnitude, I think the state of the Ethereum 2.0 chain is 7 gigabytes right now. So if you have the Ethereum 1.0, if you have a new entrant who wants to come in, for example, as a full node, as a miner, for example, they would have to download 7 gigabytes. So let's go back to the shards and see why this is especially bad. So remember, the validators, they get randomly sampled. And so from the point of view of a single validator, you will just go all over the place and create blocks in different places. But in order to create a good block, you want to be able to prioritize the transactions with respect to transaction fees to gas. And in order to do that, you need to have the state. And so, but in order to move to a new shard, you have to download all this data, and you might not have enough time if you shuffled extremely fast to download all the data. So we actually have two possible ways of dealing with the state and doing the execution. One method is the easiest is to say, okay, well, instead of shuffling the block proposers on a very frequent basis, we're just going to shuffle them infrequently. So, for example, we're going to keep them in a given shard for 30 days. So they download these gigabytes of state, and then that's their investment for the whole month. And then once they get assigned to a new shard, they'll be given a little bit of heads up, so that they'll have some time to download the state for the new shard, and then they'll be switched over to this new shard. The other approach for state execution is what we call stateless execution, where you have no state. And this is quite a cool idea, and it's a little advanced, but it's not too bad. So let me just briefly recap how state works in Ethereum 1.0. So you basically have what's called a key value store. So you have the key, which is some sort of address. This could be, let's say, for example, a 32 byte address, and then for each key you can store a value. And what we have is we have all the keys and value pairs at the bottom here. We just line them up, and then we have a process called Merkleization, where you basically hash this key value and this key value, and then you concatenate the hashes, and then you get another hash. So basically, what you do is you're building this binary tree. I mean, I'm simplifying a little bit, but basically, you're building this tree. You're building what's called a Merkle tree, and then at the very top here you have the Merkle root. Okay, and the nice thing is that this root, which is a 32 byte hash, uniquely fingerprints the whole database of state, which is these key value pairs. And one of the really nice things about this data structure is that it's very easy for someone to prove to you that some key value pair is indeed stored under this root. And the way that they do it is that they say, okay, look, here's the data, here's the key, here's the value, and it's here. And in addition to the key and the value, I'm going to give you all the hashes that are basically along the way of what's called the Merkle path. So you're going to have, it's going to provide this hash, and so with the key and the value, they can compute this hash, and so this hash becomes computable, and then they're also going to provide this hash, and then with these two, you're going to compute this, and then they provide this hash, so with these two, you compute this, and then they're going to provide this hash, and then you'll be able to check that the hash that you compute from these two does indeed match the root. Okay, so if that does match, then you prove that this corresponds to this. Perfect. Now, stateless execution is a really nice idea where the block proposers they only keep track of the root and nothing else. They forget about all of this, and the only thing they download is a root. And so syncing up to a new shard is instant, because you just need to download 32 bytes. And then the question is, where is the state? And one of the ideas is that the state is actually provided by the users themselves. So let's say that I have an Ethereum address and I have 1 Ether. Well, I know I have 1 Ether, that follow my knowledge. And so if I want to spend the 1 ether, what I'll do is that I'll look into the key value pair, and then I will I know that my ether is here, and then I will build the Merkle path, and then I'll give the Merkle path to the block proposer, and the block proposer says, yes, this is indeed a valid transaction. This data does exist. You do indeed have 1 ether because you've proven it to me cryptographically. The only thing I have is the root and your transaction, but that's fine. I don't need anything else. And I'll go execute your transaction, and then I'll move on to the next route. And so from the point of view of the block proposer, the only thing they have in memory is this root. And that solves the problem of shuffling around the shards.